When the James Webb Space Telescope first opened its golden eye, astronomers expected to see the universe's earliest days in sharp detail. They thought they'd find familiar shapes, small forming galaxies, or perhaps the bright glint of early stars. Instead, they found something they couldn't explain. Littered across the deep space of the cosmic dawn were strange, tiny red dots. They didn't look like anything we've ever seen before. These objects were incredibly bright, yet impossibly small. What makes them even more baffling is their timing. They are everywhere in the early universe, but if you look at the cosmos just 1.5 billion years later, they completely vanish. It's like they existed for a brief moment in cosmic history, only to disappear without a trace. We don't see them in our local neighborhood, which makes them a unique puzzle of the ancient past. Think about that for a second. We've spent decades building models of how the universe evolved. We thought we had a pretty good handle on the timeline, but these red dots don't fit into our neat categories. For years, astronomers built their understanding of the cosmos on the idea that things grow slowly. Galaxies take time to build, and black holes need billions of years to swallow enough gas to become supermassive. But these red dots tear up that rulebook. Standard astronomical models can't make sense of them. If these dots are galaxies, they are far too dense, packed with too many stars for their tiny size. They would be hundreds of times more compact than any galaxy we see today. If they are ordinary supermassive black holes, they are far too heavy for the early era they inhabit. We're talking about monsters that shouldn't have had enough time to grow. The data doesn't fit our neat equations, and it leaves us with a giant gap in our cosmic history. Astronomers are left scratching their heads, staring at these crimson specks that challenge everything we know about how cosmic structures form. How did they get there so fast? And why did they all disappear so suddenly? The mystery deepens when we realize that standard physics can't explain their strange properties. Some researchers believe we're looking at a completely new kind of celestial object, a hybrid that blurs the line between a star and a black hole. They call it a black hole star. It sounds like science fiction, a bizarre chimera of two opposite cosmic forces. But how could a star wrap itself around a black hole? And what did scientists see when they started digging into the light of these mysterious objects? To understand where these red dots come from, we have to look at the massive surveys that found them. Large-scale observational projects named EIGR and FRESCO scanned the early universe. They focused on a period between 500 million and 1 billion years after the Big Bang, searching for the first signals of cosmic structure. In the grand scale of cosmic time, this is the very beginning of everything we know. When astronomers looked at the data, they didn't just find a few isolated red dots. They found them in surprising numbers, scattered across the ancient sky. But why are they so incredibly red? The first place scientists look for an answer is a concept called cosmological redshift. We know that our universe is expanding. As light travels through this expanding space over billions of years, the space-time itself stretches. This stretching pulls the light waves, making their wavelengths longer. Since blue light has a short wavelength and red light has a long wavelength, this cosmic expansion shifts the light toward the red end of the spectrum. It's a bit like a siren sounding lower in pitch as it moves away from you. The further away an object is, the more its light is stretched, and the redder it looks by the time it reaches our detectors. But there's a catch. Cosmological redshift can explain why early objects look warm, but it can't explain why these specific dots are so red. The redshift of that early era should make them look a bit orange or amber, but these dots are deep saturated crimson. The math just doesn't add up on its own. So, if redshift isn't the whole story, what else is going on? The leading idea is cosmic dust. Think about a beautiful deep red sunset on Earth. The sun isn't actually changing color. Instead, our atmosphere is full of dust and gas molecules that scatter the shorter, bluer wavelengths of light away from your eyes. Only the longer, redder wavelengths can pierce through the haze. Astronomers call this dust reddening. If these early objects are wrapped in massive shrouds of cosmic dust, it would block their blue light and let only the red light escape. It's a neat explanation, and for a while it seemed to solve the puzzle. It gave astronomers a comfortable way to fit these objects into our current theories. But as they looked closer, they realized the dust theory had its own massive problems. What if the red glow isn't a trick of dust at all? What if we're looking at something much more exotic? A spectroscopic fingerprint that shouldn't exist in the early universe. To find out what was really going on inside these red dots, astronomers had to look at their light in detail. They used a highly sensitive tool on the James Webb Space Telescope called NIR-SPEC, which is a near-infrared spectrograph. This instrument splits the incoming light from a single dot into a rainbow-like spectrum, showing us exactly how much energy is emitted at each wavelength. When they looked at the spectra of these red dots, they didn't see a normal smooth curve like the ones we get from typical galaxies. Instead, they found a bizarre V-shaped fingerprint. It was a shape that shocked the astronomical community and defied their expectations. This spectrum had a lot of light at the blue and ultraviolet ends, and a huge, rising amount of light at the red and infrared ends. But in the middle, there was almost nothing. It was a steep drop followed by a sudden rise. Part of this drop was caused by a specific physical feature called the Balmer break, which happens at exactly 364.6 nanometers. This break is a classic signature of atomic hydrogen. When light passes through hydrogen, electrons jump between energy levels. The Balmer break represents the threshold where the photons have just enough energy to tear electrons completely away from hydrogen atoms. Seeing this break tells us that hot young stars are definitely there, burning bright. When scientists saw this signature, they thought they had the answer. They proposed that these red dots were actually starburst galaxies. These would be incredibly dense, compact regions where stars were forming at a furious pace. In this scenario, the blue part of the V shape comes from hot, massive newborn stars that have just burst into life. The red part of the V shape comes from the massive amount of dust that surrounds these stellar nurseries, absorbing the blue light and re-emitting it in the infrared. It was a neat model. It suggested that we were seeing the very first cosmic factories, places where stars were born in numbers we've never seen in the modern universe. For a brief moment, it felt like the mystery was solved. We were just looking at very dusty, very crowded nurseries of young stars, and we thought we could explain them with our current theories of stellar evolution. But when the math was run on these stellar nurseries, the numbers didn't just disagree. They broke the laws of physics themselves. How could a galaxy hold so much dust without collapsing under its own weight? The starburst galaxy theory seemed like a safe bet, but it didn't hold up under close inspection. In 2024, an astronomer named Caitlin Casey decided to run the math on these objects. She wanted to know if a galaxy that small could actually hold enough dust to create that extreme V-shaped spectrum. What she found was a devastating blow to the starburst theory. The calculations showed that the amount of dust you would need to block that much blue light is massive. In fact, based on the volume of stars we can see, these objects only have about 1% of the dust required. The other 99% of the dust simply isn't there, and there is no physical way to explain where it went. It's a huge mismatch that cannot be ignored. But the problems didn't stop with the dust. If you try to pack that many stars and that much dust into such a tiny space, the physical density becomes absurd. The stars would be packed so close together that they would be separated by only a few astronomical units. To put that in perspective, the distance between the Earth and the Sun is 1 astronomical unit, which is about 93 million miles. In these red dots, stars would be as close to each other as the outer planets are to our Sun. At that density, stars would constantly collide, ripping each other apart and creating a chaotic mess. We don't see any evidence of that kind of cosmic demolition derby. And then there's the telescope data. When the James Webb Space Telescope zoomed in with its highest resolution, it didn't see any structure. If these were galaxies, we should see a faint halo, a soft glow of stars spreading out around the core. We should see the shape of a spiral or an ellipse. Instead, the telescope saw only pure, unresolved points of light. They look exactly like single stars or black holes, with no host galaxy in sight. It's as if the galaxy is completely missing, leaving only a naked source of intense light. So the starburst theory collapsed under the weight of its own mathematical contradictions. The dust math doesn't work, the physical density limits don't allow it, and the high-resolution images don't show galaxies. If they aren't starbursts, then they must be black holes. But that leads us directly into another massive paradox. How can a supermassive black hole exist in the early universe without the massive galaxy that's supposed to feed it? If these red dots aren't galaxies, then they have to be active black holes. But how do we explain that weird V-shaped spectrum? Astronomers came up with a clever model to solve this. They suggested that we're looking at a supermassive black hole that is actively feeding on surrounding gas. This black hole isn't sitting out in the open. Instead, it's wrapped in a thick, donut-shaped ring of gas and dust called a torus. If we look at this torus from the side, the dust blocks the light from the hot center. The dust absorbs the blue light, but lets the red light pass through. However, some of the light escapes out of the top and bottom of the torus. This escaped light bounces off gas clouds above the black hole and reaches us as blue light. That would perfectly explain the V-shape we see in our data. The spectra also showed wide emission lines, which are called broad Balmer lines. These lines are caused by hydrogen gas moving at incredible speeds under the influence of intense gravity. The wider the line, the faster the gas is moving, and these lines were exceptionally wide. The data showed that this gas is swirling around the black hole at thousands of kilometers per second. It's a clear, undeniable sign of a gravitational monster whipping gas into a frenzy. It looked like the mystery was solved, and we had found our feeding black holes. But this model has a devastating paradox. When a supermassive black hole feeds on gas at this rate, the gas gets incredibly hot because of friction and gravity. It should emit massive amounts of high-energy radiation, specifically X-rays that can penetrate the dust and escape into space. If these red dots are feeding black holes, they should be glowing brightly in the X-ray spectrum. So, astronomers pointed our best X-ray space telescopes, like the Chandra X-ray Observatory, at these coordinates, expecting a bright signal. What did they find? Absolutely nothing. There were no X-rays at all. The data was completely blank, and there was no hint of a high-energy signal. It's a huge problem that leaves researchers baffled. You can't have a black hole feeding fast enough to create that much light without producing X-rays. It violates everything we know about how accretion disks behave. Without X-rays, the feeding black hole theory falls apart. So if it's not a dusty starburst and it's not a normal feeding black hole, then what is this red beast? The answer lies in a calculation that completely shatters our understanding of how galaxies grow. This brings us to the most shocking part of the red dot mystery, the overmassive black hole paradox. In our modern universe, there is a strict, predictable ratio between a galaxy and the supermassive black hole at its center. Typically, a black hole is only about 0.1% of the total mass of its host galaxy. This delicate balance is maintained by a process called feedback. As a black hole feeds and grows, it heats up the surrounding matter, releasing energy that blows away the gas around it. This process shuts down star formation and stops the black hole's own growth. The galaxy and the black hole evolve together in a neat, balanced relationship that has lasted for billions of years. But when astronomers calculated the mass of the black holes inside these early red dots, the ratio was completely broken. These black holes aren't 0.1% of their galaxy's mass. They are closer to 10%. That is 100 times larger than what we see in the modern universe. It means the black hole is almost as heavy as all the stars in the galaxy combined. It's like finding a human baby with a heart that weighs as much as its entire body. The proportions are completely wrong, and standard astrophysics can't explain it. This discovery breaks our understanding of cosmic coevolution. How could these black holes grow so fast without destroying their host galaxies in the process? As astrophysicist Fabio Picciucci points out, we are facing an absolute impasse in our theories. Either these black holes grew through a mechanism we don't understand, or the galaxies themselves are forming in a way that defies our models. The feedback loop that regulates black hole growth in the modern universe seems to be completely broken or absent in the early days of the cosmos, allowing these giants to feed without limits. This leaves astronomers with a profound riddle. We're looking at a population of monsters that dominated their host galaxies at the dawn of time, only to vanish as the universe aged. Did they merge to become the supermassive black holes we see today, or did they evolve into something else entirely? We don't have the answers yet, and each new image from deep space only adds to the confusion. The James Webb Space Telescope has opened a window into a chaotic alien era, and the answers we find might rewrite the history of our universe from the ground up, leaving us to wonder what else is hiding in the dark. To break the deadlock between stars and black holes, astronomers needed to scale up their observations. They couldn't rely on just a few isolated discoveries to rewrite cosmological history. They needed a map of the early universe. This is why astronomer Anna de Graaf and her team at the Harvard-Smithsonian Center for Astrophysics stepped in. They wanted to catalog the anomalies of the cosmic dawn. They designed a dedicated observational project to hunt down these red sources directly. It was named the RUBIES survey, which stands for Red Unknowns, Bright Infrared Extragalactic Survey. Between 2024 and 2025, the team used nearly 60 hours of precious Webb time to collect light spectra from 300 extremely red targets. These targets ranged in age from 650 million to 1.5 billion years after the Big Bang. Out of this massive batch, they estimated that 30 to 50 were the mysterious little red dots. At its release, it was the largest spectroscopic catalog of these objects ever assembled. De Graaf hoped this deep field analysis would bring definitive answers and clear up the confusion. Instead, the data did the exact opposite. RUBIES revealed that these bright red objects are far more diverse than anyone first assumed. When looking at simple images, they all looked like identical red points of light. But their light spectra told a different story. The catalog contains several distinct species of cosmic bodies. Some were active galactic nuclei powered by central black holes. Others were dusty star-forming galaxies. There were even massive galaxies that had stopped forming stars surprisingly early in cosmic history. It seemed that both sides of the starburst versus black hole debate were partially right. The red dots were not just one single thing, but within this diverse group, a specific subset refused to be classified. These objects still exhibited the V-shaped spectra, the broad emission lines, and the ultra-compact point source shape. Their nature resisted explanation. Then, in July 2024, the team targeted a specific point source located 11.9 billion light-years away. Its spectrum was so extreme that it stopped the researchers in their tracks. They named this anomalous object the Cliff. To understand why this object shocked the community, we have to look at how light behaves at the atomic level and what these spectral gaps are telling us. To understand the mystery of the Cliff, we must look at quantum mechanics. Think of electrons around an atom as climbers on a ladder. They can only stand on specific rungs, which represent energy levels. When a photon of light hits an electron, it carries energy. If it has the exact amount of energy needed to push the electron to a higher rung, the photon is absorbed. Every element in the universe has a unique electron configuration. This means each element absorbs light at very specific wavelengths, creating a barcode. This barcode is what we call a spectrum. For hydrogen, the most common element, the key number is 364.6 nanometers. This wavelength represents the exact energy needed to rip an electron completely off the second. Energy level. Photons with longer wavelengths don't have enough energy to do this, so they pass through the gas. But any photon with a wavelength shorter than this has plenty of energy to ionize the hydrogen, meaning it gets absorbed. This sudden drop in light creates a steep drop in the spectrum called the Balmer break. When we see a Balmer break in a distant object, it tells us there's hydrogen gas between the light source and our telescope. Usually, a large galaxy has stars of different ages and temperatures, creating a gradual, slanted break. The sharper and steeper the break, the more uniform and pure the hydrogen gas must be. But the spectrum of the Cliff was different. Its break was almost vertical. It was twice as strong as the break of any cosmic object we had ever seen in the early universe. This near-vertical cliff was a major puzzle. The spectrum sent completely mixed signals. The broad emission lines suggested gas moving at thousands of kilometers per second, which points to a supermassive black hole. But the steep Balmer break required a giant, quiet, and uniform envelope of hydrogen gas, which is the signature of a massive star. De Graaf realized that normal models couldn't explain this contradiction. She proposed that the Cliff was a hybrid object. She called it a black hole star. This hybrid model combined the physics of both worlds. But it also raised a massive question. How could a giant star hold a supermassive black hole in its core? A black hole star sounds like a concept from science fiction, but it is built on solid physical laws. Inside this hybrid body, the power source is completely different from a normal star. Our sun and other stars burn hydrogen through nuclear fusion in their cores, which pushes outward against gravity. A black hole star has no fusion. Instead, its core contains a supermassive black hole. As surrounding gas falls toward this central black hole, it gets compressed and heated to millions of degrees, releasing massive amounts of energy. This accretion energy pushes outward, supporting the giant gas envelope. From the outside, this object looks like an incredibly massive bloated star. It is shrouded in a giant sphere of hot, dense hydrogen gas. This gas envelope behaves like a stellar atmosphere, which explains the strong Balmer break observed in the Cliff. But this model also solves the mystery of the missing X-rays. Under normal conditions, An active supermassive black hole blasts out high-energy X-rays from its accretion disk. This is why astronomers were confused when the James Webb Telescope detected no X-ray signature from the little red dots. The black hole star model explains this absence. The hydrogen gas envelope surrounding the core is incredibly thick and dense. It acts as a massive shield. When high-energy X-rays are emitted from the accretion disk, they can't punch through this gas wall. Instead, the X-rays collide with the hydrogen atoms, getting absorbed completely. This energy is then reprocessed by the gas cloud and re-emitted at lower energies. It escapes the star as thermal heat and the red optical light observed by our instruments. This model explains the missing X-rays and the red color of these objects. But it also introduces another problem. To build a black hole star, you need an enormous amount of hydrogen gas concentrated in a very compact region. In the early universe, gas clouds usually cool down and fragment into normal stars. How could a massive cloud collapse directly into a single giant envelope without forming stars? First, the answer lies in the invisible infrastructure of the infant cosmos. To find out, we must look at the dark matter scaffolding that shaped the first structures of the universe. To understand how these cosmic giants formed, we must examine the dark matter halos that ruled the early universe. Dark matter is an invisible substance that makes up most of the mass in the cosmos. In the cosmic dawn, it formed a vast network of halos and filaments, like a spider web stretching across space. These halos acted as gravitational anchors, pulling in gas to form the first galaxies. However, the physical properties of these halos were not all the same. Most dark matter halos in the early universe had a high spin rate. As gas fell into these fast-rotating structures, the centrifugal force spread the matter outward. This is similar to a carnival ride where the chairs swing further away from the center as the ride spins faster. This outward drift allowed the gas to cool down slowly and fragment into smaller, isolated clouds, which eventually ignited to form individual stars. This is how normal galaxies are built. But a very small fraction of dark matter halos behaved differently. They had almost no spin. In these rare, low-spin halos, there was no centrifugal force to push the infalling matter outward. The gas didn't spread. Instead, gravity pulled everything straight toward the center in a massive, concentrated collapse. The gas remained extremely dense and compact. This super-dense environment prevented the gas from fragmenting into small stellar seeds. This was the perfect incubator for a black hole star. The sheer density of the gas allowed a central black hole to form and feed rapidly, while the rest of the gas remained bound to it in a massive, thick envelope. Mitchell Begelman's theoretical models showed that these conditions were highly specific, yet inevitable in a young universe. But if this model is correct, it means these black hole stars were not permanent features of our cosmos. They were temporary structures destined to transform. And this transformation might explain why these little red dots vanished from the universe after a few 100 million years. The theory of black hole stars sounds like a modern response to the James Webb discoveries, but its origins go back much further. In fact, it was predicted close to 2 decades ago. In 2008, theoretical astrophysicist Mitchell Begelman from the University of Colorado published a model describing these exact objects. He called them quasi-stars. Begelman's model showed how a black hole could form at the core of a dense collapsing gas cloud. Instead of blowing the gas away, the gravity of the central seed would hold the envelope bound. The quasi-star would glow, powered not by nuclear fusion, but by the energy of the black hole feeding at its center. Begelman calculated that a black hole in this configuration could grow at extraordinary rates, reaching thousands of solar masses in just a few million years. However, this growth has a limit. As the central black hole consumes gas, the outer envelope slowly expands and cools. Eventually, the envelope hits a temperature floor of around 4,000 Kelvin. At this point, the physical balance breaks. Radiation pressure wins the battle against gravity. The quasi-star envelope is violently blown away into space, ending this brief phase. What remains is a naked, supermassive black hole. Begelman argued that quasi-stars were not a permanent type of cosmic body, but a short phase in a black hole's early life, lasting only a few million years. This explains why the little red dots disappeared from our view 1.5 billion years after the Big Bang. The intense gas reservoirs needed to rebuild these envelopes simply vanished as the universe expanded. This theoretical model fits the observational data perfectly. It explains the color, the brightness, and the sudden disappearance of the red dots. But the black hole star theory does something even bigger. It solves the two most devastating paradoxes that have plagued cosmologists for decades. It changes how we weigh these monsters and how they grew so fast. To see how, we must look at the path of light itself as it travels through the dense envelope. The first paradox resolved by the black hole star is the issue of mass. Normally, astronomers measure the mass of a distant black hole by looking at the width of its spectral lines. Broader lines mean faster gas, which requires a heavier black hole to hold it in orbit. But in a black hole star, photons do not travel in a straight line. They bounce repeatedly off the dense gas envelope. Every collision shifts their wavelength slightly. This scattering makes the emission lines appear much broader than they actually are, tricking us into thinking the black hole is 100 times heavier than it is. When researchers corrected for this scattering effect, the estimated masses of these black holes drop significantly. They fit perfectly within the normal 0.1% limit. The second paradox is how these black holes grew so fast without hitting the Eddington limit. This limit is the maximum speed a black hole can feed, set by outward radiation pressure. In a black hole star, the Eddington limit is calculated based on the mass of the entire gas envelope, which is much larger. This allowed the central seed to feed at extreme speeds, bypassing the traditional limit. The black hole star model shows that these early giants were smaller than we feared, but grew faster than we thought. Yet many details remain unmapped. To trace their life cycle, we need more data. The Webb telescope has a narrow field of view, but upcoming missions like the Nancy Grace Roman Space Telescope will scan areas 100 times larger, helping us locate thousands of these objects. Ultimately, science is about rewriting the rules when a new discovery demands it. The little red dots prove that the early universe was not just a collection of young stars. It was a place of hybrid giants. If more observations confirm this theory, it means the first structures in space were built around hidden monsters. So, what do you think came first? The galaxy or the engine at its center? Let us know in the comments. And if you want to receive more signals from the deepest parts of space, subscribe to Deep Space Signal.